projectiles, there's a great deal of effort and work that goes into problem solving. So I'm going to dedicate this first lecture in problem solving section 3.6 to just the stages, the rules, and the thought process that you use to get through problem solving in projectile motion, with a little bit of Benny to help. Okay, so the first concept that you need to make sure that you're addressing every single time you solve problems is you need to make sure that when we solve for projectile motion problems, we use kinematic equations separately for the horizontal and the vertical components. You have to break them up into vectors. Right? We always assume when we're doing this that our t naught is 0, and that simplifies our equations. And we break them into their horizontal and vertical components. And with the exception of the fact that one is horizontal and the other is vertical, you're going to notice that we have the exact same components, and these are our three kinematic equations. In the horizontal direction, it'd be the velocity in the x direction would equal v naught ax t. And the y, that's the exact same equation, but in the y direction. All right, our next kinematic equation is for the horizontal version and the vertical version. They're the exact same equation, only with the direction changed. And then finally, for our last kinematic equation to consider, we have the x version and the y version. A few things will always be true in kinematics. For projectile motion, our acceleration in the x direction will always be 0, and our acceleration in the y direction will always be gravity. Why is this true? Well, it's because gravity only works in the y direction. And in the horizontal direction, there are no forces acting on the object, so there will be no acceleration. With those two givens, we can solve for any velocity with a theta relative to the positive x-axis. So what we're saying is that any velocity, whether it be this one or a velocity like this, right? Either way, when we draw them to a positive x-axis and give that theta. And as long as that theta is to the positive x-axis, then we can solve for the components. Right? The velocity in the x direction will be equal to that velocity times the cosine of theta. The velocity in the y direction will be equal to that velocity and the sine of theta. And we can break things down once we break our velocity down relative to the axis into its x and y components. And then we can take a look at the horizontal and the vertical equations with ax equals 0 applied and ay equals gravity applied. And when we know where our x component velocity and our y component velocity come from some initial velocity with some angle relative to the axis. All right, if that happens, our equation up here, if acceleration is 0, will become vx equals vx naught. Our equation on this side, if acceleration is gravity, then Vy will equal V naught y naught plus gt. And remember that that plus g is assuming that we would set our axis or give that g a negative value. Our next equation, if acceleration is 0, then x will equal x naught plus v naught t. And our y will equal y naught v naught y naught t and 1/2 gt squared, where again we either set our axis with a negative or fix our g. And then one of the things that I want you to consider is I want you to consider to be careful setting your axis every time and reflecting it with the correct values. Here I've shown you g, where the g is just some gravitational value, and depending on your coordinate system, right, if we would set every single time, if we'd set down as negative, then this equation would be Vy equals Vy naught minus gt. And here we'd set y equals y naught plus Vy naught t minus 1/2 t squared. So this is what I mean when I say set your axis every time, and you want to reflect it with the correct positive and negative values. This also matters because imagine if your initial velocity in the y direction were some negative value, then it'd be y naught minus vy naught t. So make sure that you're doing that. We can further simplify these equations if we assume that x naught equals 0 and y naught equals 0. Right? We can simplify these equations even further. For example, this equation up here, x equals x naught plus v naught t, if that's a 0, then x is just going to equal vx naught t. And on this side, if we assume y naught is 0, then it becomes y equals vy naught t plus 1/2 gt squared. Alright, so setting your axis and simplifying your equations as much as possible gives you a really good start to this type of problem solving. So once you start your problem solving, you're going to follow a pretty straightforward system. In fact, this system of problem solving is the exact same system that you used for solving kinematics in section 2.6, and you probably already have it in notes. So you probably don't need to recopy everything from the textbook for problem solving projectile motion. You probably only want to focus on what's a little bit different about projectile motion as opposed to solving for regular kinematic problems in one dimension. For example, solving for problems in 2 dimensions requires creativity, and you have to think pretty hard about what you're doing and what things look like in the situation, which means that you're going to have to work a little bit when you solve problems in 2 dimensions. It's not just following the rules. You're going to need to be careful to avoid just plugging in numbers that seem to maybe work. You need to know what's going on. You need to be able to think about it. You need to be able to imagine it. If that's been done, then we start with the first rule of problem solving. Read the problem, organize all of the information, and then you want to make sure once all the information is organized, you need to decide what's the system, what's the time interval, and how are you going to move forward to solve the problem. Once you've read and organized and made some decisions, you're going to draw a diagram that includes absolutely everything. That diagram needs to show what happened to the object during the entire time that you studied the object. Right? You want to draw the path of the projectile. You want to draw the forces that were acting on it. You don't want to just draw some butterfly and let us assume what its motion is. You want to draw it out. You also need to make sure to choose your origin and your x and y axis system, coordinate system. It's really important that you do this immediately once the problem is drawn, because this will have an effect on the sign of all of your values, and you're going to need to be really consistent with it. Otherwise, you're going to get completely inexplicably wrong answers. So make sure to set your origin and choose your xy axis system. Remember, whenever possible, to set your origin so that your x naught and y naught can be 0 if possible. If it makes sense in the problem, it simplifies your equations. Once you've set your coordinate system, you're going to consider your time interval that you're studying. All right, you want to focus on the time that gravity is acting on the object, where gravity is the only force. Remember, you can't think about the time when a ball is in the hand. You can't think about the time when the ball has hit the ground. You have to think about when it's in free fall. Because free fall is the only instance where projectile motion is actually happening. If it's not in free fall, it's something other than projectile motion. Number 5, you want to examine horizontal and vertical motion separately. Oh, and there's this other thing that I wanted to point out, is that when you're solving the problem, make sure that the x values and the y values match, that they make sense and that they go together. Remember, the connecting point between x and y is the time. So if you solve for a time from the y pilot, you better make sure that that time is the time that you needed for the x pilot. right? Make sure that your values match. Then examine the horizontal and vertical motion separately. Just like I said, you want to separate the equations of the y pilot from the equations from the x pilot. At this point in time, if you haven't already, you need to make sure if you're given a v0 to find the x and the y components of that velocity. Stay organized, right? You have a diagram, you've thought the situation through, you have a bunch of knowns. You want to list your knowns separately, knowns for the horizontal section, knowns for the vertical section. Make sure that when you're doing projectile motion problems that ax equals 0 and ay equals gravity, and that your coordinate system matches your signs. Right, you want to match your positives and negatives to your coordinate system. So if your gravity is in a downward direction, you're going to modify your equations to reflect that downward acceleration. A few things to remember is that Vx is constant, Vy is 0 at the highest point along the pathway. So if you've got an object that follows a projection pathway here at the highest point, your Vy is going to equal 0, and that's always going to be true. That's why something stopped moving upward. Its velocity became 0, and then it changed going down. And another thing to consider is the velocity before an object lands usually isn't 0, right? It's falling due to gravity, so that means it's getting faster and faster and faster as it reaches the ground, which means in all likelihood that the velocity that you're experiencing down at the bottom isn't going to be 0, so you probably shouldn't set it to 0. And last but not least in your problem solving is think things through and organize before you solve. A little bit of planning, a little bit of structure to your problem solving is going to go a long way. And it's a heck of a lot better than having 6 pieces of papers with random numbers written on them, and then as soon as you feel like you got lost or made a mistake, there's no way to follow the path back to where you started. You're going to be completely lost. So, now that we have our basic rules for problem solving, let's take a look at some example problems. Alright, so we're going to start with example 3-4 on page 57, which is driving off of a cliff. I'm going to be using the exact same numbers as the problem in the book does, but I'm going to be changing things up to make it a little more interesting. Alright, so first things first. We want to look. And the problem is that a strange cat drives in its human's vehicle horizontally off a cliff. Only a strange cat would do that. The cliff is a 50-meter high cliff. We want to know how fast must the cat be going to hit the ground below 90 meters from the base of the cliff. Where Benny is waiting. And after the cat makes it down to Benny, they plan to drive off in the sunset together. So we're going to focus on our problem solving. And then for this problem solving, we have to decide that our object is the cat and the cat's car. And the situation is, here is a cliff of some 50 meters high, right? And Benny is waiting. some 90 meters away. And here's the cat. Driving its owner's vehicle. And it's going to drive horizontally off of the cliff. And we want that cat to make it all the way there before it hits the ground. Alright, so that means, by logic, we need to set an origin. Alright, so I'm going to set, this is positive y, and this is positive x, which means if I set this as my origin right here, that down here at the bottom is going to be negative 50.0 meters from the top, and this is going to be some positive 90 meters. And since down is negative, that means that gravity is down, so gravity is going to be negative. And we can break our problem up into x and y components now. Alright, so x components and y components, x pilot and y pilot. Since acceleration in the x direction is 0, I know that displacement, and I set my origin there, so my x naught equals 0. So my displacement is going to be equal to the initial velocity in the x direction times time. And I know that my displacement that my cat would like to have is 90.0 meters from the base of the cliff. And I'm going to need to find my v naught x, which will equal the initial velocity. And I know that because the cat is driving the human's vehicle horizontally off the cliff. So that means that the v naught is equal to vx naught. So those are my givens and my find for v naught. Notice I don't have t. I don't know this value yet. But good news is there's also a y pilot, and the y pilot is going to give us, and then I've set down as negative, so it's going to be negative 1/2 gt squared. And I set ay equals g, y naught equals 0. And I'm going to need g to equal 9.8 meters per second squared, and we're headed down, which is where that negative value comes from. So I can rewrite this equation as y equals v naught y. Oh, wait, v naught y, it's being driven horizontally off of a cliff. That's 0, so that means that this whole value is gone. So y is going to equal negative 1/2 gt squared. Alright, that seems pretty dandy. Alright, so now, why do we need to know this? Well, because the y pilot says we're going down! And that means that the y pilot decides this time right here, which the x pilot needs to know, because the x pilot needs to know how long is it going to have to drive that 90 meters. So, solving this, we know that time is going to equal the square root of 2y over a negative g. And I can plug that in over here because I have the equation 90.0 meters is going to equal v naught x times t, which t is the square root of 2y over negative g. And I can plug in those values, so 90 meters is going to equal v naught x times the square root of 2 times a negative 50 meters, because we decided the final position was 50 meters below the origin, divided by a negative 9.8 meters per second squared. And lucky us, the negative up here and the negative down there cancel out. And so the problem becomes 90.0 meters is going to be equal to V naught x times, and we can resolve what's inside of square root. So we have 2 times 50 divided by 9.8. And we can do square root of that value, which is 3.19 seconds. 3.19 seconds. And we solve for V naught x is going to equal 90.0 meters divided by 3.19 seconds. So 90.0 meters divided by 3.19 seconds gives us 28.2 meters per second. Alright, that was the find that we had. It was 28.2 meters per second. That's how fast the cat needs to be going in order to make it all the way to Benny, and then Benny climbs into the car and they drive off into the sunset together. You've lost your cat and your car. No explanation of why, but Benny did manage to say as you were driving off into the sunset, I'll be back. But he didn't say anything about your cat. Sorry, bro. So now we have taken a look at one example of using the problem-solving system to answer a particular question. There's so many different questions that we could ask about projectile motion. So let's take a look at another one. A kicked football. This is example 3.5. Alright, so example 3.5 says that a football is kicked at an angle of 37 degrees with an initial velocity of 20 meters per second. So I'm going to say that this football was for sure kicked by Benny. Alright, and there's Benny's freakishly long foot that kicks said football. Alright, and said football is kicked at an angle of 37 degrees from the positive x-axis with an initial velocity of 20 meters per second. So this is a fun game for Benny, but we need to take a look at what the problem is going to ask us to solve for. First, it wants us to solve for the maximum displacement in the y direction, the maximum height. Then it wants us to solve for the time before the football hits the ground. Now, one of the things I know is that these two don't match, right? These two aren't the same time, aren't the same interval. So I'm going to be breaking my problem down a little bit. Another thing that I'm going to need to solve for is I'm going to need to solve for its displacement when it hits the ground. Ground, not ground. And then, one thing I do want to point out is that these two are the same interval. And then D, I want to solve for the velocity at the maximum height. And E, I want to solve for the acceleration vector at the maximum height. Don't ask, I don't know what this is. So these are all of the things that I'm going to need to solve for when Benny kicks the football. So let's go ahead and let's draw out a diagram that includes everything that we could possibly need. By the way, there's a lot of similarities between this and the lab, but we're not 100% there yet. So this is what the ball is going to do. Right? The ball is going to get kicked up. The angle there is 37 degrees because velocity and displacement always happen in the same direction. The ball, we need to set our axis, so I'm going to say that up is a positive y, and I'm going to say that over is a positive x, and that this is our displacement x, which is an unknown value. But that means that right here is our y max, right? Our y value at the highest point. And I'm going to set my origin so that this is the origin. Alright, so that means that over here, y naught is going to be 0. And over here at the end, y is going to be 0. Alright, because they're both along the x-intercept. So we know that they're both going to be equal to 0. So, looking at this, I can tell you that the total time in the air is going to be determined by y. Right? So t, the total time, is going to be determined by the y pilot. So x and y. X, right, we know that ax equals 0. We're going to set the origin to 0. And we know that the velocity in the x direction is going to be given by the x component of this vector. So that means it's going to be equal to the initial velocity times the cosine of theta. So that means that Vx naught is going to be equal to 20 meters per second times the cosine of 37 degrees. And my equation is x equals V naught x times t. So I could solve for this if I knew time. And I know that time is going to be determined by the y pilot. The y pilot says we're going down! And the y pilot knows that the initial velocity is going to be given by the initial velocity sine theta. Alright, because it's the y component of the initial velocity. And it knows that the acceleration in the y direction is going to be given by g. And we also know that the position is going to be equal to, we set the origin right there, so we know that y naught equals 0. And so it's going to be given by Vy naught t minus 1/2 gt squared. And that negative came from the fact that gravity is down, and down we decided it was a negative direction. So there are two time intervals to consider. For time interval number 1 is the amount of time that it takes to get here. Alright, and for that interval, we are not going to be resolving anything in the x direction because the only x value we want is all the way over here. So that means that everything we solve for y max, we're not going to worry about what's happening in the x direction. We're only going to worry about what the maximum height is. So interval number 1 is going to be given, we need to find the y value right there. So we're going to call that y1 for interval number 1. And what do we know about the max height? Well, one of the things that we know is the reason it's the max height is because the velocity in the y direction right there is 0. And the initial velocity happened over here, so we know that the initial velocity is going to be equal to V naught sine theta in the y direction. We don't care about x here because the only thing we need to know about this interval is the maximum height. And since these are our values, and we also know that negative g equals a, that means that the most useful equation for us to use is going to be Vy squared equals V naught y squared minus 2Gy. And the reason is because we don't really need to know the time it took it to get to the top, because we only need time to solve for our x component. We're not interested in the x halfway across. So we're only interested in that height, and we know the relationship between initial and final velocity with gravity using this equation. So I can solve for V naught sine theta is going to be 20 meters per second times the sine of 37, which is going to be I write it down, 12 meters per second. And I know that the final velocity is 0, so 0 equals 12 meters per second squared minus 2 times 9.8 meters per second squared times y. Sorry, I went out of frame a little bit there. Alright, and that's just plugging in my variables there. So now I get that 144, that's 12 squared, right? Meters per second is going to be equal to 19.6, and that's going to be meters squared per second squared is going to be equal to 19.6 meters per second squared times y. So when I solve for y, I am going to get 7.35 meters. Right? And that is how high up in the y direction. So that's the first interval. Now, important thing to note is that I don't need to resolve anything else for this instance in time, because there's no x relationships that I need to resolve here. So now I can start resolving for the other time interval in the problem, and the other time interval in the problem is the time it hits the ground. Alright, so my x and my y components are still going to be correct. These are still my equations. Here's where the relationship of time is going to be important. Right? I know that I need to find this. I am given Vx naught, and I need time. And I'm going to find that time from the y, which y equals Vy naught t minus 1/2 gt squared. Now, V naught x is going to be equal to V naught cosine of 37. And when I solve for V naught cosine of 37, I'm going to get 16 meters per second. So that's 20 meters per second times the cosine of 37 equals 16.0 meters per second. So that means that x will equal 16.0 meters per second, and then whatever time is over here. So that means that I need my y value. Well, I decided up here that my y value is 0 because I'm back to the x-axis. I also know that my Vy naught was equal to V naught sine theta, which was 12 meters per second. And I know that g is 9.8 meters per second. So I get 0 equals 12.0 meters per second times time. Minus 1/2 of 9.8 is 4.9 meters per second squared times time squared. Now, I don't need to quadratic this, I can factor it. So that means that I have 12 meters per second minus 4.9 meters per second squared times time equals 0. So my time equals 0 seconds, and my time equals 2.45 seconds. Solving for within here. Alright, so that's going to be 12 divided by 4.9, and I got 2.45 seconds. So these two time intervals represent the time over here and the time over there, the two times that the parabola crossed the intersection of the x-axis. So now I have my time. I can take my time and I can plug it in over here. So I have 16 times 2.45 seconds, and I get that my displacement is 39.2 meters. So let's go back and let's check our organization. What have we solved for? We found y max. Y max was 7.35 meters. We found the time before it hit the ground. We found that to be 2.45 seconds. We found the x when it hit the ground. That was 39.2 meters. The velocity at y max, well, my max was right here. We actually used that when we solved. The velocity at the maximum height is always going to be in the y direction 0. So if it's at this maximum time, if Vy equals 0 and Vx is constant, right? We said that Vx is constant, and that means the velocity at the max would be V0 y plus V0 x added together vectorially is going to be 16.0 meters per second horizontally at the top. And then acceleration at the top, well, acceleration, the only acceleration that's happening is the acceleration due to gravity, and that's completely down, so that means that the vector is going to be a g downward, and that would be a 9.8 meter per second squared valued vector right there. So we've successfully solved for every single portion of this problem of a kicked football, just by breaking it down into interval number 1 and interval number 2 and thinking about our principles of kinematics. I'm going to go ahead and allow you guys to think about this as you solve through. There's a few conceptual examples that we can use and we can think through, and then there's also going to be the range equation, and that will finish out our section 3.6 for projectiles.